Hello every professors and doctors. Now I will introduce my paper named Cross-Scale Imperfect Data-Based Composite H-Infinite Control of Nonlinear Two-Time Scale System. My name is Wang Haoyu, is an associate professor from China University of Mining and Technology. The paper is introduced a section as follows. Nonlinear two-time scale systems are a class of high-order systems with fast and slow dynamic coupling, which widely exist in motor systems, process industries, and other fields. External disturbances are inevitable for actual systems. Thereby, it's of great significance to desire robust controller for nonlinear TDS systems to suppress the adverse effects of disturbances. H-infinite control performs as an effective method to solve the robust control problem, which can make the system meet a precise disturbance index. In recent years, researchers have obtained abundant results on the H-infinite control of nonlinear TDS systems. However, these methods based on explicit system dynamics, which was difficult to satisfy in actual situation. Reinforcement learning, as known as ADP, is proposed by Verbs and has grown into a powerful tool to deal with optimal control problems. Forward in time for systems with unknown dynamics. By executing the information interaction between neural network, approximate structure, and controlled system, the process of value function, evaluation, and control method update can be iteratively performed. Reinforcement methods assisted by system decomposition have made headway in solving optimal controller problems for nonlinear TDS systems. Due to the existence of time-scale parameter, ill-conditioned problems may appear in the iteration learning process. General nonlinear TDS systems with fine channel disturbance in both fast and slow dynamics have not been addressed, which proves the current research. Consider a class of nonlinear TDS system whose state space model is described by EQ1A and EQ1B. Real industry system consists of multiple subsystems, often of high system order, which may exhibit dynamics changes on different time scales. TDS systems featured by the time scale parameter to quantify the discrepancy between fast and slow dynamics can more depict the interplay between fast and slow dynamics. This capability makes it more suitable for modeling such complex systems and providing deep picture of internal dynamics. Zero-wire established analysis and control theory for TTS systems, including fine-order and reduced-order decomposition methods, which can effectively avoid high-dimension and ill-conditioned problems. For System 1 under Assumption 1 and 2, find a state feedback controller. The system decomposition method has been proved to be an effective method to reduce the controller desired complexity of TTS system. Hence, when we now derive the slow and fast subsystems based on time-scale decomposition principle. For the fast system 6, design a state feedback controller such that the closed loop fast system is stable and has L2 less than or equal to gamma F. Regarding the fast H infinite problem as a zero-sum differential game problem, the H infinite problems can be viewed as a two-player zero-sum game problem. For the slow subset system 5, we aim to find a state feedback controller such that the closed loop slow subsystem is stable and has L2 gain less than or equal to gamma S. There exist two main bottlenecks for designing fast and slow H infinite controllers based on the idea of system decomposition for TTS system. First, the performance matrix of the two sub-problems after decomposition are non-quadrate and contain cross-coupling terms of the system state inputs and disturbance, which brings great difficulty to the analytical solution of the controller. Second, the decomposition process involves the separation of Auroral perturbation level gamma. In this section, the state reconstruction matrices incorporation cross-scale information is given to deal with the unmeasurability of substate states. We can use the slow state x1 and fast state x2 of the original TTS system to reconstruct virtual slow substate x1s and virtual fast subsystem state x2f. By incorporating cross-scale interaction information x1 and us state reconstruction machinist is developed to reconstruct the unmeasurable first substate. Then the weight of the first controller is updated as follow EQ27. Data reconstruction method is probed and applied to control data for subsequent reinforcement-based composite H-infinite control. Hence, cross-scale information interaction is reflected in the data reconstruction process of fast and slow substate systems, meaning to amend the bias caused by the time-scale decomposition. And the block method is depicted in Figure 3. Okay, the proposed composite H-infinite control method is applied to the PMSM system and verified on the dispatch-based PMSM flatboard. The components of the experiment device are shown in the figure 5. Our method achieves the super tracking performance, requires less response time, and inhibits better robustness against external disturbances. We consider the control of fast states ID and IQ, so the PSSM inhibits weak DQ currents. In this paper, by using the SPT and reinforcement learning, the composite H-infinite control of nonlinear TTL system was investigated in course of cross-scale imperfect data and unknown slow dynamics. The original H-infinite control problem was decomposite and reshaped as two standard subproblems. To develop the reinforcement learning method for two subproblems, we proposed the cross-scale data reconstruction method to solve the problem of perfect measurement of subsystem states. Exponent result on PSM system illustrated the effectiveness of our proposed method. Okay, thank you.